So it has, I've got a script on one side. I've opened here the first example, I think. Um, and
Yeah.
then I've got the workspace over here, and you should, once you've downloaded the example files, go to the file browser in MATLAB and make sure that you browse to the file location where you downloaded your files.
Mhm.
So you can see them in the file in the current folder. Um, and so first I was just going to sort of walk through an example data set, but there's maybe some, um, I hope, some general principles that we can talk through along the way. But it would be helpful if maybe it's most helpful if this is interactive and actually focused on what you um, need to learn about EMG filtering. So it's helpful to know what your what past background, what past experience you have with filtering in general. What do you know about filters? So we can talk about filtering principles as well. So I'm going to just stop sharing so I can see your faces and stuff. How much experience do you have with filters previously? Have you used them? Have you written your own code?
I have not.
You have not. Okay. Um, how many of you have heard of a Bodie plot? No? And is Vanson there? Can you? I don't know if Vanson's in a position to respond or not.
Yeah, sorry, I was
Have
trying
you?
to download the files.
Okay, but have you ever heard of a Bodie plot?
I have not.
Okay, we're going to start there. All right. So, filter design, we're probably you've all seen plots of data over time, right? But filter design, you don't, we often don't look at it this way when we're actually just implementing filters, but it is sort of like the basis of the theory in the background. All of the data is transformed into the frequency domain rather than in being operated on in the time domain. And I'm not going to go into all of the theory about that, but basically, any signal, right? Theoretically, you can reconstruct that signal from a series of sine waves, right? A sum of a series of sine waves at different frequencies and amplitudes, right? And filter design is basically based around that concept. And the filter has the specification that it basically gets rid of the frequencies in certain specified ranges and allows a pass through unchanged the components that are in another what is called the pass band, right? And so if you were actually taking a theory class on filter design, a lot of that would revolve around Bodie plots and understanding the frequency domain. I'm going to see if I can do like a whiteboard. I am terrible at drawing on whiteboards, but we're going to just try it. If I can do one more. Whiteboards, new whiteboard. Can you see my whiteboard?
Mhm.
All right.
Yes.
So a Bodie plot, I'm just going to basically, there are two components to a Bodie plot. One looks at the magnitude of the filtered signal as a function of frequency. So we would have magnitude, I'm going to just call M, and frequency in hertz, right? And basically, you have a frequency that is the original magnitude of the original signal. We're going to just like normalize hypothetically here to 1, right? Is the original signal, right? And so if the filter allows all of the signal at that frequency through, then our frequency response of the filter will be at 1, meaning there's no attenuation of frequencies of the signal at that frequency. Okay. And this is plotted as a function of frequency. And so basically, you just imagine that you have reconstructed the original signal um, with sine waves of various frequencies, right? You can plot the original data using that. You can actually do that on the original data and plot the results, which we can maybe work up to. But hypothetically, you can do that for any signal, right? And what a filter does is if you, so the terms that you will see with filters are like, can I do a text box here? Because I am terrible at writing. High pass, low pass, and band pass. This terminology can be a little bit confusing. High pass means you filter out low frequencies and you pass through high frequencies, right? Okay. So you use a high pass filter. For example, if you have motion artifact at low frequencies, but your actual signal is at higher frequencies, right? A low pass filter filters out high frequencies and passes through low frequencies. Okay. And a band pass applies both a high pass filter and a low pass filter on the same data, right? And so it passes through a specified frequency band. And that's why it's called, there's a band pass, right? So we can talk about, so you need to know something about the frequency characteristics of your signal and the likely frequency characteristics of the noise that you're trying to filter out of that signal, right? And so some common sources of noise that we have to deal with in filtering, right, are motion artifact. This is something like sometimes when we have EMG electrodes on people or EMG wires, it's more problematic with wired systems because wires act as an antenna, and when they move, that causes an motion artifact in the signal. So you can pick up motion artifact. Those would typically be at the frequency ranges of the motion, and so they're at lower frequencies, like below 25 hertz. The other common source of noise that you would find in many signals is the just electrical noise by picking up the AC line voltage, which is at 50 hertz or 60 hertz, depending on which country you live in, right? Here it's 60 hertz, in the UK it's 50 hertz. But that means that you would have a characteristic noise that's oscillating around that frequency in the signal, okay? Another source of noise that you might encounter is if you are getting interference from some kind of radio signal. So we've had this problem when we had a very strong local radio station near our lab. And so we were picking up the actual radio broadcast signals in the EMG recordings, which is a real pain in the ass. And we basically had to, they were so big and so strong, they made a new building that was, the entire building was turned into a Faraday cage to try to insulate from those signals. But another source that's more common in our setups is that if we are measuring sonomicrometry at the same time as EMG, the sonomicrometry system is sending ultrasound noise into the body, which the EMG signal can pick up. And so you will sometimes have those frequencies. They tend to be frequencies. I can't remember, Lauren, if you remember offhand what those frequencies tend to be, but they're higher, like, I'm going to say above 1,000, maybe something like that. So you need to know something about your signal and what kinds of things you're trying to filter out and keep in your signal. So what do we want to keep in? So like common sources of noise we've mentioned, right, is motion, 60 hertz electrical, radio, and ultrasound. What we also need to know is what's the physiologically relevant range of the signal we're actually trying to measure, right? And for EMG, that relates to the frequency characteristics of action potentials. And that is, for very slow ones, unfortunately, that overlaps with some of our sources of noise. So slow action potentials can be as slow as 20 hertz, right? So there is data at like the 20 hertz, but we can, for our purposes, sometimes say, well, we think that the physiological range is actually more like, um, 90 hertz to 450 hertz or something like that. Okay. Or very slow. Okay. So when we're doing designing filters, what this would look like, what a low pass filter would look like in a Bodie plot would be, you are trying to pass through frequencies at a certain specified range. And then a perfect filter, you'd basically say, okay, I'm interested in frequencies above 60 hertz, maybe, right? And above that frequency, I don't want to filter anything out, so I'm keeping it all in. And below that frequency, I completely cut it out so that it's out down to zero, right? So it would be like a perfect square wave. But in reality, it's impossible to design filters that are perfect square waves. They don't have a perfect, you would have to have like a filter with an infinite number of terms in it, which gets unruly. So when we specify filters, we specify the filter cutoff frequency and we specify a filter order. The filter order, the higher the filter order, the sharper that it more closely approximates this kind of like square wave shape. The lower the order, the more it looks kind of just like a gradual signal like this. What that means is that you may be filtering out some of the data that's actually in your relevant frequency range, and you may not be getting rid of all of the noise. But there's a trade-off because as you get filter orders of higher and higher order, it tends to introduce artifacts into your filtered signal. So you can get weird things like you might be filtering a force signal that maybe it goes from 0 up to a peak and then back down to 0. If you have a really high filter order that's trying to approximate things with too high an order of filter, it might do something like this to your data where it like adds some weird artifacts in there. And so that's something to look out for. Basically, filters can introduce artifacts into your data, especially if you are using filters that are too constrained in their filter order cutoff frequencies. And the reason you might need a sharp filter is that you might have a case where the actual signal is very close in frequency to the noise. But if that's not the case, then it's better to use a lower order filter in general because they end up providing smoother results with fewer artifacts. So that's an example, oops, sorry, what did I do? I started erasing everything. Okay, I'm gonna start again here, but I'm gonna go, okay, my graph. I don't know how to use this thing very well. Hey, where did my drawing pencil go? It disappeared.
Uh-oh, now I have one.
I think I have one too.
Oh, I think you're drawing. You're drawing now. I don't know. Maybe only one of us can draw at a time.
We can go like this. Mhm.
Okay. You're drawing it again. So
One.
when we filter EMG, you need to know something about how the data was collected. And you need to know, for example, if there was already filtering in hardware, because there often is some, right? And so if there was some filtering in hardware, that might reduce the need for you to filter it in software, right? And you need to know your original sampling frequency. So if we're gonna, I still don't have my tool back for some reason, but so I'm a little confused about that. Why can't I? Hmm. Hmm. What happens if I add a page? Do I get all my tools there? No. Okay. Well, um, can you switch to a different tool? If you switch to a different tool, does it give me my tool back?
I switched mine, so I shouldn't have one anymore.
Yeah, I switched.
You switched,
Yeah.
and you can still see the pen tool
Mine
on
doesn't
your.
more.
That's so bizarre. Okay.
You
Why
can
did you
maybe
take away?
you can go into the top right corner and then you can maybe change the participants can edit and that we can have cursors and just maybe that would only give you the ability to use them.
But it doesn't seem to change which tools are available for some reason. Okay, I'm gonna just try again. New whiteboard. Okay, I'm starting again. Okay, so we're gonna go back to the same graph here.
Mhm.
Just quickly, frequency in hertz. Okay, so what we're going to do is compare some different filtering settings for filtering EMG from an example data set. This data set is like a little too clean to be a good example almost, but it's what I had handy, so we'll just use it anyway. But we're going to design a high pass filter, okay, which means, like we said, we're going to filter out low frequencies and keep high frequencies. And then we'll compare that to a band pass filter where we have a band. So the filter design is going to look something like this, right? Where we're filtering out low frequencies, we're keeping some specified frequency range, and we're filtering out high frequencies, okay? And we're also going to look at the frequency composition of the original data compared to our filter design. Okay? So I'm going to go to the data. So if you want to follow along, you'll want to make sure you downloaded the code and then open the first example file. And I'll step through to make sure everybody can follow. This has a weird warning when I open this file, but it's okay, so don't worry about that. I think it's just an artifact of how it was saved originally. This is data from Caitlin Beamis's most recent data collection. So here, I'm going to share my desktop again. Okay, can you see my two MATLAB windows again?
Yes.
All right. Okay. So I have just evaluated the first two real lines here, okay, to load the data. You get a warning, but don't worry about that. What you should see is within your workspace, a data table that we're going to pull EMG data from. Okay. So let me know when you got there and that you confirm that you're able to successfully load the data. And if you wanted to just double click on that data, you can see the entire data table. It's got a lot of things, but we're just going to pull out columns 7 and 8, which are the EMG channels, to have a look at the EMG data and practice filtering. Did it load for you? It does print some warnings, but just don't worry about those warnings.
Got it.
Okay. So you should always confirm this before hard coding a variable, but you would confirm it in this case by looking at the time vector. And you can take, but so I know that the sample frequency is 5,000 hertz here. Okay. You can, if in some cases, calculate it directly from the time vector, but sometimes it's not recorded, so you need to know it from your notebook or something like that. One thing to note is that when you're designing the filters in MATLAB, it always works from normalized frequencies, and the frequencies are normalized based on what's called the Nyquist frequency. The Nyquist frequency is the sample frequency divided by 2. And so it's that Nyquist frequency is like the theoretical limit of what frequencies you can analyze from a given data set. You can't reconstruct anything about a signal above the Nyquist frequency, okay, without more sophisticated methods. There are modern methods that even can try to do that, but we're operating using techniques that operate based on the Nyquist frequency, okay? So we're line 16 to 19 here, just pulling the data out of that data table so that they're just in the format of a standard array in MATLAB, and then creating a time vector for reference later. So I'm going to just go ahead and highlight line 16 to 17 and evaluate them. Oops, actually go up to 13, evaluate all the way from 13. Okay, so we want to make sure we set the sampling rate, create our EMG data array. So now you can see after evaluating those lines, I have an EMG data array that is just it's an n by 2 double, where n is the number of time points in the original data set, okay? And 2 is for the 2 EMG columns. So the next line here is just getting information about the total number of samples and the total number of channels of my EMG data in case I needed to, operate in a loop to process them separately or things like that. Now we're going to start specifying the characteristics of our filter, okay? And you can play around with this on your own and see what happens when you, adjust these frequencies. So we're going to use some tools in some functions in MATLAB. But.ord designs a filter, a Butterworth filter, and it specifies the order and cutoff frequency needed based on specified stop band and pass band characteristics, okay? So the stop band is, right, above the stop band, you want to get rid of all of the signal, okay? And the pass band is, right, sorry, we're doing a high pass filter. So above the pass band, you want to keep all the signal. Below the stop band, you want to remove all of the signal, okay? If it were a low pass filter, it'd be the other way around, okay? But so stop band means that's the frequencies you want to filter out. If it's high pass, then it's below that frequency, you filter it out. If it's low pass, then it's above that frequency, you filter it out. The pass band is the frequencies that you want to make sure that you maintain. And the reason that these aren't the same is because it's impossible to create a completely vertical filter, right? So this is specifying basically how wide is that window where the filter is attenuating the signal and it's not all the way at 1 or all the way at 0, okay? And the function filter order allows you to figure out what filter order and cutoff frequency gives you that filter performance. Okay. Now, it is also possible to just directly specify your filter order and your cutoff frequency. And those are the things that you'll see reported in papers. So you might like recreate results from papers by specifying those, but it gives you less insight into what your filter is actually doing, right? In terms of the actual frequencies kept and filtered out. So these attenuation, this RS is stop band attenuation. So by how many decibels does the signal get attenuated in the stop band? 40 is a lot. That should be like basically removing it. And the passband ripple, basically there's some basically remaining artifacts in the passband, and it's specifying how small those need to be. But these are pretty standard values. The actual default values, I think, are 40 and 3, but you can read more about those in the help if you're interested. So I'm just going to evaluate lines 30 to 36 here, or no, sorry, 27 to 36. Oh, I need to go higher. I should have just done it by sections, right? I'm going to just run the whole section, which you can do too. But then we'll walk through the different results. So first, we're specifying our stop band and pass band frequency. I've put the stop band at 30 to remove all motion artifact associated with movement, right? And the pass band at 90. Just because I want to, if there's any 60 hertz noise, I want to filter that out, but I want to keep the low, motor, like the slow motor unit action potential activity as much as I can, right? If you then, you've got to normalize these frequencies to the Nyquist frequency, which is the sample frequency divided by 2. So that's what this part is doing. And then the output of this function is the filter order, right? And the cutoff frequency that I need to get that filter performance. So that cutoff frequency is in normalized units. If we go, so I've recalculated it in hertz by multiplying it back by the Nyquist frequency, and you can see that the effective cutoff frequency is 75. So it's telling me to get the performance I specified, I need a Butterworth filter of order 5 and cutoff frequency of 75 hertz. Okay. And then you apply the filter using the function filtFilt. You put in the outputs of this butter function, right? B and A are simply the filter coefficients that were designed to meet the specifications. And then you put this into filtFilt with your EMG data, and you get your raw data, your filtered data out, okay, as the output. I'm not plotting it yet because I was going to plot them all together, but you could go ahead and do a quick plot if you want of your, just can work up to that. Figure, sorry, I mean to type figure. If we just want to plot some of our filtered data and our raw data, overlay it into the same plot, we can do a quick plot. Can you see my plot? Okay, as I said, the data were almost too clean. So you have to zoom in to see the difference between the filtered and the raw data. And so if you zoom in, what's the main difference you can see here?
Just looks like they're offset from each other.
Yeah, so mainly the original raw in black had an offset so it wasn't centered around 0. It had a DC offset. If you apply a high pass filter, it always removes the DC offset.
Hmm.
So that's important to note, right? Because that DC offset is basically a low frequency component of 0 hertz, right? That is getting removed. Okay, so this was a pretty clean signal to begin with. So it didn't really change much. If you look here where there's a lot of action, you can see the baseline is pretty clean. Sometimes you see a lot more noise. It turns out that this one did have a 60 hertz notch filter in hardware. So it did minimize some of the noise in the data collection. Okay, so what about, so that's the high pass filter, okay? In this case, it's just mainly removing the DC offset. It doesn't change things, but we could play around with different filter settings and see how it changes the output. And I encourage you to do that to get an intuition about how filters work. Because you will also find that if you try to make these two frequencies too close, you'll get to a point where it can't actually create a filter that meets those specifications. So let's say I was like really like concerned that there's real data at like the 60 hertz range or something like that. And I tried to make that a lot sharper. So let's say we want the passband to be 40 hertz rather than 90 hertz. And we can go and just rerun this. I'm going to just make this part its own section, right? So we can rerun this section with different filtering settings, okay? And okay, it still calculated the result in this case, so that's good. If you zoom in, you'll see that this one looks even more similar to the original. There's even less difference between the original and the raw data. But now if we look at what our cutoff frequency is in the filter order, oops, the actual calculated cutoff frequency in hertz. In this case, it's doing a filter order of 19 and a cutoff frequency of 38 to get that result. Usually there's no reason to do that unless you really have good sound reasoning for it, right? Because people tend to recommend that you use the lowest order filter that's adequate for your data set because of the potential for it to introduce artifacts into the signal.
Monica,
Yeah.
if you're using something with that high of an order, like, is that reliable data? Or do you?
I mean, it doesn't have anything to do with the raw data, right? This is just a filtering choice, but you can see, I mean, I think it's important to look at your filtered and your raw data and compare them, right? And see if you're getting something weird that doesn't look real that you've introduced into the signal, right? That's the main thing, is like do a reality check every time. You know, if I'm zooming in on this does not look problematic to me because it seems to be following the original data pretty, you know, accurately. So I'm not worried. I wish I had like a bad example to show you, but I would say where you typically see the most obvious problems are when a signal, rather than going sort of like symmetrically above and below 0, if you have a signal that goes from like 0 to a sharp kind of peak and then back to 0 and a sharp peak, what you might see is that in your filtered data, if you are using a high order filter, you will see it go below 0 and then up again. And so we'll introduce time points where the filtered data goes below 0, even though that was not in the original data. And if you
Mhm.
see that, that's a problem because that is actually introducing something, a feature into the data that wasn't originally there. So that's the thing to look out for. One thing you'll note, if you look in the literature, you'll see that people often rectify EMG signals because the positive versus negative spikes aren't meaningful, right? And so they just show the rectified EMG. It's important to not, so don't do your high pass filter after rectifying. That will introduce some weird artifacts because that's when you'll get, because the whole signal is now above 0, then you'll filter it with the high pass filter. It may reintroduce cases where it goes below 0 because it's trying to fit that weird shape, right? So when you are doing EMG filtering, the steps are to high pass or band pass filter the original raw data, right? Then you can rectify it if you want to just show the the signal in the positive only. So we can walk through. That's what different sections of this actually do. So there are some cases where you might want to band pass filter EMG. And so I'm showing an example of a band pass filter just for reference. The cases where you would most likely want to band pass filter is, for example, you might be getting interference from another signal that has higher frequency components, like an ultrasound signal or something like that, right? So in the bandpass case, it's a little bit counterintuitive how you specify these filter settings. So that's why I wanted to provide an example. So if you look here at lines 54 and 55, I'm now specifying rather than one frequency for the stop band, there are 2 frequencies, okay? So you can, right now it's set to below 30 Hertz and above 1200 Hertz. So that's just saying, this is like, if I had a case where I knew that there was some ultrasound interference that was in the sort of like 1500 Hertz range or something like that, right? I might want to filter that out. So here I'm specifying stop band 30 and 1200. The pass band, now remember the pass band is the signal, the range of the data you want to keep, right? Make sure you keep. And so we can specify, I have that at 90 here to 800. You could go narrower than that, but it doesn't, there's no, if there's no noise that's likely to be picked up at this sort of like higher frequency end, then you don't need to make that band too tight, basically. So I've specified it as 800. We again need to normalize them based on the Nyquist frequency. And then when you're running these same functions, see, I'm specifying the same functions, but in this case, if you are using a bandpass filter, then it automatically knows it's a bandpass filter if you have 2 frequency inputs for the parameters, okay? So if I run this section, so we've got now our stop band frequency has 2 numbers and our bandpass frequency. Then when we input these normalized frequencies into our Butterworth filter order function, we should get, okay, we get a filter order of 9. And then our cutoff frequencies are 83 and 855, essentially, right? So again, the filter order is like how sharp does that filter roll off, right, at around the cutoff frequencies. And if you were looking at this on a Bodie plot, Just go back to the Bodie plot concept again real quick. Can you see the whiteboard? Did it just pop up? Okay. Plotting these. This would be a bandpass filter. Your cutoff frequencies occur sort of right at the middle of that, the slope where the frequencies are rolling off, right? So the pass band would be like here, right? The stop would be like so: pass, P, stop, S, S, stop, and these would be the cutoff frequencies, C. Okay. So your cutoff frequency is always going to be between your pass band and your stop band frequencies, in the middle of this sort of roll off of that filter that you designed. Okay. So one other concept that's important. So we're going to plot the data. Let's go ahead and plot the data for our band pass results. Can you see the graph? Okay. So if we zoom in, one thing you might notice in this one compared to the previous one is that the band pass filter is attenuating the amplitudes of the spikes a little bit more than the original high pass filter did. And the extent to which it does that depends on how much real high frequency data there is in the signal relative to the band pass frequency characteristics you specified. So we can play around with this. If you change this value, you could definitely make it so that there was a more obvious problem with your band pass filter if you make those frequencies too low. So if we just run this one. Oops, I ran the whole thing. I didn't mean to read, jumping ahead here. I meant to run this section only. So as you change those bandpass frequency characteristics, you'll get more pronounced attenuation of those higher frequency spikes, okay? And so that's another, it's good to just look at your data and see if you make that too low, right? So that's why it's important not to just use filter settings that other people have reported in the literature, but actually like adjust the filter settings and look at your data and see how it looks in filtering your data. So if we run this section again, so if we put them low enough, you can see that there's obvious attenuation of real signal here, right? And if you zoom in, you can see that the green one, the filtered one, is kind of lower frequency in characteristic. It's less, the spikes are less sharp, right? And that's because of the band pass filter, right? So because we've put the filter for the higher frequencies too low, so it's now attenuating that signal and getting rid of some signal that's actually the real physiological signal. So this is also something that you would want to look at if you're filtering force data, for example. Force data is different from EMG data in that you are typically running a low pass filter on the data to get rid of motion artifact and electrical noise from the force data. But there are real higher frequency characteristics in force data for example, around heel strike impact that actually do have some higher frequency components. And so when you're specifying your filters, if you're doing force data, you need to be careful that you look at your filter settings carefully, that it's not getting rid of some of the real force data in the signal that might be relevant to your question, depending on what kind of question you're asking. Okay, so we've done a band pass filter. I'm going to put it back at some more reasonable values. What did I have originally? 1200 and 800. This is something I learned, through trial and error, because if you look at the frequency settings that people mostly use for human EMG data, it's lower frequencies than this. And I realized that guinea fowl muscles have higher frequency components than human muscles. So, which isn't terribly surprising, I suppose. Right? They are smaller, but okay. So I'm reasonably happy with this version, okay, where it's mainly removed the DC offset of the signal. And if we zoom in here, even though it's attenuating some of those peaks slightly, it still retains the overall characteristics of the curve, right? So that's what I'm looking for there. The other thing you'll often see in the literature on in EMG analysis is rectifying the EMG and then doing another low pass filter on the data. And this might be confusing because it's like, well, why? I just filtered the data, why do I need to filter it again? But the purpose of this version of the filter is very different. In this case, you're trying to basically estimate muscle activation characteristics or the time course of muscle activation based on the EMG signal, okay? So because we know that action potentials have this high frequency component, right? But muscles have excitation contraction coupling that have basically smooth out effectively the development of forces at lower frequencies because of the delay associated with excitation contraction coupling. And so people have used a low pass Butterworth filter on the rectified signal to create what they call a smoothed linear envelope, which basically approximates the timing of muscle activation from the EMG signal. So the steps in doing that, you would want to do whatever filtering you need to on the original raw data before you rectify it. That might be a high pass filter or a band pass filter, right? Depending. Here I'm just putting the high pass filter data because we don't really have any noise of note up in the higher frequencies in this signal. And then I'm calculating a new Butterworth filter design that is at 10 Hertz. So I'm normalizing 10 Hertz by the Nyquist frequency. And I'm just using a second order, specifying a second order filter with a cutoff frequency of 10 Hertz. So notice I'm not going through all of the steps of the filter design because I already know this is based on standard approaches in the literature on creating the linear envelope. To use it's a standard approach is to use a fourth order low pass filter with a 10 Hertz cutoff. Okay. And different people might use slightly different values for that, but you could look in the literature to see. Although I said fourth order, I'm putting it as a second order in here because when you run the function filt, it runs the filter forward and backwards on the same signal. And the resulting order is twice the original order. So if you run filt using a second order filter design, the resulting order is 4. Now that's a little bit confusing, but okay, so if I run that section, I'm just basically running this filter on my rectified EMG. And now I'm going to plot the results in a big tiled plot for all of the things that we've done, okay? So we can see them all side by side. So this is just the data as a function of time. The top contains our raw data and the high pass filtered versions. Channel 1 is on the left, channel 2 is on the right. You can see that channel 2, that muscle is much more active in whatever behavior we're measuring here, which is balancing on an unstable perch. And then the middle panel has the band pass filtered characteristics, and the bottom panel has our linear envelope with the rectified signal. Okay. So if we zoom in, I've also used the function link axes. So if I go and zoom in on one graph, the X scaling will be maintained between the graphs. And so you can see this magenta colored curve is approximating the timing of activation, right? That's what's called a smooth linear envelope. Notice that it misses some important features though, if you want to be picky. It doesn't accurately capture these bursts here, right? And so one of the criticisms of this smooth linear envelope approach is that you are in fact applying a low pass filter to the data, which therefore attenuates high frequency components of the signal more than lower frequency components of the signal. So it actually better approximates the timing of the slower action potential components compared to any fast action potential components. And I don't have an example ready today, but one of the ways around that is that there's a different approach to calculating a linear envelope using wavelets, where you use a bank of filters rather than just a single filter. And that bank of filters are wavelets that are designed to match the frequency, the range of physiological frequencies of action potentials in muscle, from around 20 hertz all the way up to 450 hertz. So you get this bank of wavelets, and you can calculate from that. You basically use each wavelet to do a band pass filter on the data, and then you sum the magnitudes across all of those wavelets to get your smooth linear envelope across all frequencies. And then if you did that, it should capture the activation associated with these little bursts as well as like the general time course of activation for the whole cycle. All right. Do you have specific questions or specific tasks you're trying to accomplish with your data analysis?
I admittedly have not been focused on EMG in a couple months, so I just
Mhm.
came for general
Just
enlightenment.
general, yeah.
But
Well,
I-
if any of you are interested in doing like trying the wavelet technique on your data, we could do another session later on in the summer and actually run that on the data. It's something that can be useful if you're interested in the frequency composition of the motor, and the distribution of potential action potentials from slow to fast, and whether or not that changes in your data for different tasks as well. But it's a little bit more advanced in terms of a filtering technique, right?
Yeah. I think I'd be interested in doing that because I've been interested in, I guess, like muscle fatigue and the time course of that. And I feel like
Yeah.
the wavelet analysis on that in viewing like throughout an activity, how does the frequency profile of the EMG signal change in relationship to like the activity
Yeah.
that somebody's doing? I think that's really interesting. So I think it would be cool to have a session on how to actually
On that.
extract like the frequency profile, especially from like, I guess the benefits of, you can like this data coming from the birds is, I think, how do you use surface EMG signals and how confident can you really be on
Mhm. Oh, you're cutting
human
off a little bit.
EMGs versus like getting them
Mhm.
when you're like actually implanting them into the muscle tissue.
Yeah,
But
so
I
one
think a
thing you'll
wavelet
notice,
analysis. Oh,
yeah, the frequency distributions will be a little bit different from surface
mm,
EMG versus indwelling EMG. Um,
yeah.
and
Like, how do you, I guess, make sure that you're correctly characterizing those profiles with surface EMGs?
I think you have to accept that there are going to be some limitations. So, for example, in the data I just showed you, we sampled at 5,000 hertz.
Mm,
Usually with the surface EMGs, you're going at like
mm,
1,000 or 2,000 hertz. So you're not going to get, you're potentially losing some of the high frequency components.
mm,
Um, but in general, you know, I think that there's been shown to be a reasonably good correspondence between surface EMGs and indwelling electrodes, but the problems you have to deal with there are crosstalk between muscles, potentially, right? And you will get a slightly different signal depending on how close you are to, the actual like, um, you know, where the nerve is interfacing with the muscle itself, right? The motor end plate with the muscle. So one way that people get around the crosstalk issue is if, I mean, and we don't do this per se, but there are things called high density electrode arrays where you can basically have like multiple electrodes, like a big array of electrodes on the muscle. And then if you have that, then people can actually like decompose the different components, much like you do with EEG, right? With EEG, you put
mm,
this array of electrodes on your head, and then you basically try to decompose the different spatial components based on that array of
mm,
electrodes rather than interpreting the individual electrodes, right? But in EMG, we typically don't do that because usually you can, based on anatomical knowledge and placement of the electrodes, isolate things pretty well.
mhm,
So, but that's, something that you kind of have to, like, if you're really, really, if it's really important that exactly the frequency composition and from individual muscles, you might have to do indwelling electrodes, right?
Yeah.
And it's possible to do indwelling electrodes in humans, but we
mm.
typically try to avoid it because it's, more invasive
Yeah.
and it hurts. Yeah.
Yeah.
For the high density EMGs,
Hmm.
can you like create almost like a pseudo one if you just have like bipolar electrodes and space them in an arrangement to where they're almost like a high density array?
I suppose you could get, I mean, the more you can put more electrodes on and then
Yeah.
do, some decomposition of the components that measure from them. Like look at the core, you'd basically be doing an analysis where you're looking at, the degree of correlation between the different pairings of electrodes, right? And then
Mm,
doing a decomposition to try to get at the underlying components based on all of that
mm,
analysis. So I'm not sure what the minimum would be to get, but I feel like if I were just to guess, I feel like you'd need at least 8 electrodes to get a meaningful decomposition. And that sounds like a
mm,
pain,
mhm,
unless you're explicitly working with high density electrode arrays. And then that
mm.
system would come with software that helps you with the decomposition process and stuff like
Does
that
it?
too,
Yeah.
right? So you wouldn't have to invent it from scratch.
Mm,
Um,
I'm just curious.
yeah. I do have an example from Delsys data as my example too, if you want to go through that. But basically, it's exactly the same process, but on data that was
Mm,
collected using the wireless system. Um,
mm.
if you want to open that file and look at it. But I mean, you've seen that kind of data plenty of times before, right? But if you want to, you can go ahead and open example 2. I don't know how long this office hour is supposed to go, but you know, we could try to do wavelet analysis today if we wanted to.
I'm fine.
That would be me coding on the fly, but
I was just wondering, I know there's a way to turn your like EMG signal then straight into like frequency on the X and then the magnitude, or like I guess
oh yeah, we
the
didn't go through
amount
that
of
part
the
of my
total
script.
signal. And like would that be
Where'd it go?
considered like, in another word, like the fast Fourier transformation sort of thing?
Yeah, I forgot.
Is that
I
the
had a whole
same?
section of my script that I didn't go through that does that. If you want to go through and look at that real quick.
Like, cause if you like didn't know what frequency components or noise you had, like there
Yeah,
would be a way to
there's a way to look at that. So let's do
plot
that.
it and
So
understand. I see. Yeah.
yeah, so this is the bottom of the script has this. So we can look at the data in the frequency domain. Okay. So the details here, like basically I'm just getting the inputs necessary to do a fast Fourier transform and plot the results. So FFT is the fast Fourier transform function in MATLAB. And I'm basically calculating the FFT and then getting a magnitude from that. So you can look up the help and read more about the FFT function if you want. So if you look at this part of the script, basically what this is doing is it's getting the FFT on the actual data, and then also it's getting the filter frequency response from the bandpass filter that we created earlier too, so that we can look at both the actual data in one plot and then the actual like frequency characteristics of the filter we designed in another plot. I couldn't get them to scale exactly the same way, which is annoying me. But I'm going to just run this section. You can step through if you have any questions about the steps, we can go through that. But if I run this section, so can you see this graph?
Yeah.
All right. So the blue is the frequency distribution of the original EMG data, raw EMG data. And then I've overlaid with lines the specified stop band and pass band frequency characteristics. And I tried to lock these axes, but then I couldn't figure out why it's putting them on a linear scale on one and a log scale on the other. I don't know why. I didn't have time to troubleshoot all of that. But the lines mean the same things on both, right? So in the raw data here, you can see that my cutoffs here, right, for the low, the high pass cutoff is, these are really tight around a specified frequency range. And if I zoom in here, you can actually see evidence that a notch filter was used in the data, right? Because you can see this dip here at 60 Hertz, right? So there is real frequency content across that range, and it has a dip at 60 Hertz, which indicates that a notch filter was used to attenuate frequencies at that specific frequency, right? So you can kind of see a signature of the hardware filter in the data there. But then the peak of the real data, right, you can kind of see is sort of around the lower frequencies of the passband range, but you can still see there's real content at higher frequencies as well. if you are getting into designing filters, you might want to go and look into decibels as a unit because they're kind of confusing. Um,
Yeah, what does it mean to have some of the signal frequencies are like in the negative decibel range?
oh, the
What sense?
decibels. I mean, yeah, I don't have a good handle on decibel magnitudes, but like it's not a linear scaling, it's a log
Log?
based scaling. Um,
Um,
and so I can't remember like orders of magnitude in decibels. Like, um, oh, decibels are kind of confusing, but anyway, it's like
negative. Um,
two signals whose levels differ by 1 decibel have a power ratio of 10 to the 1/10.
10 to like, 1.
Um, change in power by a factor of 10 corresponds to a 10 decibel change in level.
Mm.
Um, it's a standard unit used in frequency, but it's not one that I typically use. So it's a little confusing. But they also do hearing tests in decibels, right? Um,
Yeah.
but the main thing to think about is like, okay, where do you see the most of your data, the real
Mm.
data, and how does that correspond to the cutoff filters you've set?
Mm.
And then here, this is the showing the design of the actual filter. You can see that it's going into the negative decibel range as well. But I think once you're getting down to like um, 40 decibels below like the original magnitude, you're basically getting rid of almost everything in that signal.
Mm. Mm.
So I don't think it's like super meaningful. Here we have, this is like magnitude 40 up here. Once we get to around 0, that's like, there's nothing really there of note, right? In terms of magnitude. So if you have more complex, it might be useful to set this one aside for now and then go look at the other data set for comparison.
Mm.
Um, we can. We open example 2. Okay. Um, do you have this example 2 file? If you
Yeah.
open up example 2,
Mhm.
okay, I'm just gonna run the first section, load the data. So you can see it has cleared my workspace and now I just have the new data in the workspace. This is from Vicon and Delsys data collection in the human performance lab. So, and then in this case, we have 8 EMG channels from the Delsys EMG system. It's a wireless system. And this one actually has band pass filtering in hardware. And I don't remember the exact frequency characteristics, but it is a pretty strong band pass filter. So you don't get a lot of um, like noise from electrical signal noise and other sources. So in this case, the main thing you want to do is remove potential motion artifact from the sensors moving on the body, for example, that might have, if that introduced any crosstalk, and the DC offset in the signal. And so here, if we kind of know, in this case, the nature of the frequency of the motion artifact we want to filter out, we might just take a simpler approach to filtering because this has a bandpass filter in the hardware. So in this case, I'm just specifying the filter order is 2, the cutoff frequency is 25 hertz, and running a high pass filter on it. Okay. Section. Did I freeze again? Oh my gosh.
My end.
Huh? My computer's about to crash again.
Oh, wait. Yeah, you froze.
Yeah.
Oh,
I'm not sure that I can force it to stop sharing because my computer crashed. Okay. Well, sorry about the technical difficulties with my computer.
It's okay.
That's good to know that it's not, that I can't rely upon it for Zoom stuff anymore. All right, well, we'll wrap up for today. Sorry, my computer decided it was done for today, apparently.
Thank you.
Yeah. All right. Well, thanks for coming. I saw somebody else logged in and then logged back out without chiming in. I feel like I hope that they weren't too intimidated to join.
Oh,
Oh well.
they maybe had to run now.
All right. Well, I'll see you all later. Thanks.
Thank
Thank
you.
you.
Bye.